Hello, this video is the first video in a series of organic chemistry videos, and the goal of these videos is to provide some intuition on organic chemistry and also go over some topics that you would see in a typical organic chemistry course, but with more emphasis on the motivation behind concepts and also application of the concepts. All right, so before we get started, let's ask the typical question: what is organic chemistry? Okay, so I assume you've had a time to think about that. And in general, organic chemistry, as you probably learned in the general chemistry course, is just a branch of chemistry that studies molecules made of carbon. So for example, these are several organic chemistry molecules, and they're all molecules that have carbon atoms as well as hydrogen atoms and some oxygen atoms, and also nitrogen. And in general, organic chemistry studies compounds that just have a wide variety of elements in them. They have a wide variety of properties, and there are just so many molecules that are involved in the field of organic chemistry, and that make organic chemistry a really important field to study. What some people tend to forget, though, is that organic chemistry is not just the study of organic molecules, and it isn't a discrete field of study, and in fact has many shared topics with other fields of science and chemistry. So for example, you might not think of seeing metals a lot in organic chemistry. However, organometallic chemistry is a very important and growing field of chemistry. And so just keep in mind that when you think about organic chemistry, it's not only the study of compounds containing carbon and hydrogen and other similarly common elements, but also the study of elements or the study of compounds that have organic components but can also interact with inorganic components, such as these metallic elements right here. So now let's get into why I study organic chemistry, and this is sort of the motivation behind studying this topic. Now, there are many reasons why people need to study organic chemistry. If you want to become a doctor, you need to study organic chemistry to understand the compounds inside of the human body. If you want to go into industry, you need to study organic chemistry to understand how certain compounds are synthesized. And in general, you will have to study organic chemistry if you want to go into a field that even deals remote with chemistry. So as some examples, again, if you want to go into biology and biochemistry, you would need to understand organic molecules that are present inside the human body, such as serotonin right here. If you want to go into pharmaceuticals, you want to understand drugs and how they are involved in organic chemistry. Lots of drugs that are used today were synthesized in the previous century using concepts in organic chemistry. So you can see that there is a very applicable component to organic chemistry. And lastly, polymers are sort of a subfield of organic chemistry, and nowadays it's even a field on its own. But essentially, if you want to understand polymers, which make up a lot of the materials in the world today, you would need to understand the principles of organic chemistry. Okay, so now let's move on to what you need to know in order to study organic chemistry. And basically, all you need is general chemistry level knowledge. You don't need to know any advanced physical chemistry, inorganic chemistry. All you need to know is general AP chemistry, or even just general high school chemistry. So first, you want to make sure that you are comfortable with Lewis structures, because we will be drawing lots of Lewis structures, such as this one right here. You also need to be familiar with bonding and orbitals, because in organic chemistry, we will deal with lots of bonds between carbon and other atoms, and also double and triple bonds. So you will need to understand that, because we will be applying that to understand certain trends in organic chemistry. You also need to understand periodic trends for that same reason. And lastly, you need to understand some concepts of equilibrium, such as acid-base equilibrium, kinetics, and also basic thermochemistry, such as enthalpy, entropy, and free energy, because those will be important for analyzing organic chemistry reactions and why they produce the products that they do. All right, so before we get into our first few organic chemistry topics, just as a reminder, in this video series, I will be using organic chemistry by Clayton to teach the material. However, if you want to learn organic chemistry on your own, it's your first time learning organic chemistry, Clayton is a little bit advanced, and so I'd recommend starting with other sources, such as Klein Organic Chemistry and also Wade Organic Chemistry. Clayton is much more advanced, but these textbooks are more suited for the beginner in organic chemistry. So depending on your comfort level with these topics, feel free to start studying with either textbook. And now let's move on ahead to sort of how you should be thinking about chemistry when you study organic chemistry. So organic chemists, again, typically deal with compounds containing carbon, hydrogen, nitrogen, oxygen, and those will be the elements that you want to be most familiar with when you study organic chemistry. But again, you do also want to be familiar with these elements in red right here. And elements in orange are important, but to a lesser extent. And in general, you want to basically understand the properties of these elements and also trends, such as electronegativity, size, radius, all that good stuff from general chemistry. All right, with that, we get into our first topic is organic chemistry notation. So here is a very complex molecule called paleotoxin. It is, as you can probably tell, a very poison, and has this very complicated structure. And in order to actually understand this molecule, we need to be able to discern its structure and also see what atoms compose this structure. And so to do that, we will need to learn organic chemistry notation, specifically called bond line notation. So if we think back to Lewis structures, we would draw a compound like this, where we indicate every carbon atom, every hydrogen atom, basically every atom that appears in the molecule, and also whether double bonds or triple bonds exists. In organic chemistry, however, this will get really tedious for really large molecules. So instead, we will introduce a concept called bond line notation, which reduces the amount of clutter you see. And some general notes for bond line notation. You want to draw atoms as zigzags. You want each vertex to represent a carbon atom, so you wouldn't have to draw like a carbon atom here, and so on. And lastly, the hydrogens attached to each carbon atom are omitted. So for example, there would be 2 hydrogens here, but we don't need to draw them because that is the convention of bond line structure, and it allows us to save time when drawing molecules and to also reduce the amount of clutter. A few other rules about bond line notation. You want to draw all hydrogen atoms bonded to atoms other than carbon. So for example, this hydrogen atom needs to be drawn because it's bonded to oxygen. And lastly, any atom that is not a carbon atom should be explicitly written out. So for example, the oxygen right here and right here should all be explicitly drawn. So essentially, to go from Lewis structure to bond line structure, so here's Lewis structure, you essentially replace all the carbon atoms with just the vertex, omit all the hydrogens bound to the carbon atoms, and make sure to include all other atoms. So you'll get this result here. So it's good to get practice on this. So let's do a real quick practice problem here. I'll give you guys a chance to probably think about this. You should probably pause the video and try this on your own to draw the bond line structure. And afterwards, we'll go over this. So I assume you've had the chance to get a shot at this. So we'll take a look at the answer. Here, you can see that we have essentially replaced vertices replace carbon atoms with vertices. And one thing that you might want to note is that these terminal carbon atoms and their hydrogens are still drawn. And this is completely due to preference. You could omit these these methyl groups circled in green, and just have a line like this. However, sometimes it is clear to also draw each group, each terminating carbon group. And that is just to clarify that you didn't make a mistake anything when you were drawing this compound, and that you indeed intend for there to be a carbon atom with 3 hydrogen atoms at this terminating branch. All right, and one last topic to set us up before we get into more specific topics in organic chemistry in the next video are functional groups. And so functional groups are basically anything that is not just a carbon-carbon single bond or a carbon-hydrogen bond. And these functional groups are important because they allow for a variety of compounds with different properties and also different reactivities. Now, the best way to sort of learn these functional groups is not necessarily just to memorize them and memorize them sort of the hard way. The best way to think about them is in terms of oxidation states. So if you remember from general chemistry, an atom that has a positive charge or has lost an electron has a +1 oxidation state. So for example, the atom Na plus has a 1+ oxidation state. The atom chloride Cl- has a 1- oxidation state. And in this case, we'll be thinking about oxidation state of each central carbon. So each of these carbons and so on. So let's just take a quick example. So for the aldehyde oxidation level, we can see that each of these central carbons has 2 bonds to electronegative atoms, namely oxygen. And you might wonder what alkynes are doing in this class. And that is because alkynes can undergo reactions that do not involve oxidation or reduction to convert into these functional groups. So you can, as an exercise, try to calculate the oxidation state for these carbon atoms that I circled, and also do it for these other functional groups to verify their oxidation states. And this way, you can then have a more methodical way of learning these functional groups. All right, so that's the video for this week. I will see you in the next video, where we will talk about our first organic chemistry topic and focus more on geometry and also stereoisomers. See you then.